Hello everybody, in this video we will discuss relative acidity of alpha hydrogens. So let's quick recap. So which one would be our alpha carbon atom? So the alpha carbon atom would be the carbon atom that is right next to your functional group carbonyl. In this case, we have two possible alpha carbon atoms. One alpha to this carbonyl. This one here is also going to be alpha to this carbonyl and also alpha to this carbonyl. This one here is going to be alpha to this carbonyl right here. Okay, so it turns out the acidity of this alpha hydrogen is around 17. However, the acidity of this particular alpha hydrogen is way higher. So you see here the pKa value almost close to 9, 8.9. So lower the pKa, higher the acidity. Now the question is why? So why this one is more acidic? Well, to be precise, this alpha hydrogen is a lot more acidic. Obviously, you can calculate the acidity of this alpha hydrogen, which should be around 16 to 20, but this particular one is a lot more acidic. So here is why. So the way we decide acidity is by looking at their conjugate base. So what happened once that acidic hydrogen is gone? Hydrogen is gone. So what is the conjugate base looks like? So if I take out this particular hydrogen atoms, what's left over? Left over is the other color. The leftover is CH2 minus. No, CH2 minus COH. So now we know that this negative charge can be delocalized with the CO pi bond. All right. So when that happens, we can create a resonance contributing structure where the negative charge becomes the double bond, the pi electron, and O minus. So in general, if you look at the hybrid structure, that's basically how the structure looks like. It's going to be hybrid of these two. Okay. So we have two resonance contributing structure here. So the more stable your conjugate base is, the more acidic the corresponding hydrogen will be. So it turns out the conjugate base here, so I'm going to draw the conjugate base here, CH3, CO. So here we're going to get CH minus, CO, CH3. So we can delocalize this negative charge to the left side. So I'm going to draw a structure here. So I can have a situations that look like this, where the negative charge is delocalized across the CO bond to the left side. And you can do the same as well to the right side. So why would the carbonyl group to the right side get left out? It shouldn't get left out, right? So this one could also be shared. So we can also delocalize our electron to the right side. So we can bring this negative charge here, move this double bond here, move this pi electron back to oxygen. So you can have a third contributing structures where the negative charge can be delocalized to the right side carbonyl group, CH double bond, CO minus, CH3. So you can have basically three resonance contributing structures. So here we got three resonance contributing structures. Here only two. So when we have more resonance contributing structure, so more resonance contributing structures, so more contributing structures means more stable. More contributing structure equals more stable. And we know that more stable a conjugate base is, the more acidic the corresponding hydrogen would be. So which is why the compound that is going to be more acidic is this one. So this one would be our more acidic. Why? Because we could draw three contributing structures here on the right sides. Okay, so that was the explanations. More stable the base, and if more stable the base is, more acidic the hydrogen will be. All right, so let's draw a couple of more things. um, let's do one more examples. So let's say we got this CS3 CO CH CO CS3 versus, okay, there is gonna be a hydrogen here. This hydrogens versus, I'm gonna do something like this. Okay, so we have two different alpha hydrogens that I want you to guess who would have higher acidity or lower pKa. So you will find out. So let's guess. So here, once the alpha hydrogen is gone, so I'm gonna draw the conjugate base here. Conjugate base. So the conjugate base, once the alpha hydrogen is gone, you're gonna have CS3 CO CH minus CO CS3. So you notice here this negative charge can be delocalized to the left side and delocalized to the right side. Okay, that makes sense. So we got two choices. How about on this side, on bottom here? The corresponding conjugate base would be CS3. Oh, I forgot that it's an ester. OCO CH minus COOCH3. Okay, if you look at here, this negative charge can also be delocalized with carbonyl, but so here's the problem. So if we go back our previous video, part 1 of this series, we noticed that ester is, the carbonyl in ester is already having a friend, already taking some burden of this lone pair, right? So here, every time it's connected to an ester, the negative charge here, it's gonna be less shareable with the CO pi bond. So when you have esters, it is less acidic. So it is connected here. So this negative charge here is connected to two esters. So it is connected. So this one is connected to two esters, right? So we got carbonyl from esters to the left and to the right. And here it's connected to two from either aldehyde or ketone. So when it's aldehyde or ketone, that's better. So ester is worse, connected to two esters, versus is connected to two ketone. So ketone is better. So you can, so this one is better. So if something is better and more stable, corresponding conjugate acid is going to be our more acidic. So this one here is going to be more acidic. Okay, so it's more acidic. So you can always correlate depending upon how many ketones. So more ketones, so if you have two ketones or two aldehyde, that's better in comparison to two esters or okay, so you make sure you compare apple to apple, right? So if you have this CH3 CO OCH3, so this is alpha carbon atoms, right? Versus this. Versus this. So which one would be more acidic? This one here. Okay, I'm gonna draw this out. Okay, who is gonna be more acidic in this scenario? So here, once the hydrogen is gone, there will be a negative charge. This negative charge can be delocalized with CO group. So you always compare apples to apple, oranges to oranges. So delocalization with one carbonyl is always less efficient when you have two. So two is better. So here you can delocalize once this hydrogen is gone, there will be a negative charge. And then this negative charge can be delocalized to the left side. It can also be delocalized to the right side. So two ester is always better than one esters. Same thing here. Two aldehydes are always better than one aldehyde. Same thing, two ketones, like two ketones or aldehyde is better than one aldehyde or ketones. And which one here? In this particular example, two ketones are always better than, wait, not that one. So here, which did were here? So two ketone is always better than two ester. So which one is gonna be here the good, more acidic here? Okay, this one would be more acidic. If we have something like this, so these are two alpha hydrogens. So we got two ketones. So two ketone is always better than two esters. So these alpha hydrogens are more acidic. So these are more acidic than here. So ketone or aldehyde are better than esters, more acidic in summary. Okay, let's stop here.